Hello again, this is Claudio from expertfea.com, recording for you the fourth webinar meant to help you improve your finite element analysis and Ansys Workbench skills. Firstly, I will invite you to access our website, expertfea.com, which is very oftenly updated. With tutorials, a gallery with solved FEA scenarios, our book, the webinars page, and of course the contact page. Also, you can visit our YouTube channel, which contains lots of videos with FEA results, which can be very helpful for you. So, today's scenario that we will analyze will be that of, let's say, high-speed stamping done with the help of an explicit dynamics analysis. So, let's assign our materials by double-clicking Engineering Data, activating Engineering Data Sources, and from General Nonlinear Materials Library we will add the aluminum alloy nonlinear and copper alloy nonlinear. We can exit the engineering data. Now we will import our geometry. Right click, import, and we will double click the model. Now the geometry is being imported. So let's take a look at the assembly. We will perform a section view. And see the punch that will penetrate the copper or aluminum part and the die. So for the piece we will assign first the copper alloy nonlinear, we'll look on the contacts. We can right click contacts, rename based on definition. The body contact punch to piece is not needed because we already have by default assigned the body interaction, which is frictionless between all body parts. As I said, we will delete this contact. Regarding this second contact, from the target we will subtract the fillet area with Ctrl pressed. Alright, regarding the mesh, we need to achieve very small solving times, and this is done by prescribing, let's say, -100 relevance, and on the sizing tab we will change the smoothing from high to low. Let's create the default mesh. Let's make also the punch to be as meshed with tetrahedron elements. And let's refine the sizing of the elements in the piece. Let's change the units to millimeters and assess a proper element size. So around 2 millimeters will be very good for us. So we will select the part, sizing, and prescribe 2 millimeters. Right click, update. So we have around 3,000 nodes, which is very good. The piece is refined. So moving next, we will apply a velocity from the initial conditions and the punch, of course, along axis Z. Let's change the units to meters, and it's 250 meters per second. So we need to fix the die. And to define an end time. We know that the velocity is 250 meters per second, and we need the punch to travel, let's say, this entire distance, 0.05 meters, let's say. So I have made a rule of thumb, let's say, if the punch travels 250 meters in 1 second, then in what time it will travel 0.05 meters. If we perform this calculation, we will obtain 0.2 seconds as an end time. But if, because we have this this part as an obstacle, it's advisable to prescribe a slightly higher value. So for the end time, we will prescribe 0.0003 seconds. This is pretty much all. On the directional deformation, we're interested in seeing the displacement of the punch on the z-axis. Also, let's see its speed. On z-axis. We can save the FEA and solve it. If we click solution information, we will see that the FEA is done in less than 1 minute. And we can change from server output to, let's say, energy conservation. And we see that the energy error, which is very important for us, is very low, let's say. The energy error is prescribed by default here. And it should not be exceeded this value. So, waiting for the analysis to finish, what I can see is that we will also change from the copper alloy to aluminum alloy and, let's say, observe the differences. In explicit dynamics, a high number of nodes, meaning a high number of equations, can lead very fast to very high solving time. This is why we chose a very coarse mesh, let's say, except the copper part. So the FEA finished. It is very helpful to manipulate the assembly in Ansys Workbench, either by pressing Ctrl and middle mouse for pen, or just scrolling the middle mouse for zoom, or pressing middle mouse for rotate, let's say. So, a short animation. Which looks very nice. Let's change the units to millimeters. The punch traveled around 47 millimeters. And the material got very thin and broke, let's say. So, this is the strain. Let's scope only the copper part. Right click, evaluate for results. As expected, the strain is very high on the copper material. Also the stress is very high. Let's see the speed of the punch. You see, it was very high at first, then as it tried to deform and penetrate the copper part, it decreased very much, more than half, from 250 meters per second to 105 meters per second. So we can stop. Let's see what happens if we change the material of the piece to aluminum alloy nonlinear and solve the FEA again. The solving time is the same. Of course that if you would like to see only a fraction of the scenario, you can modify the end time with let's say prescribing smaller values, or you can see further what happens if you increase this value. Of course, any change in the end time increases the solving time of the FEA. So the energy error is very low also. We can, let's say, rarefy this plot by prescribing here, instead of all to display points, a certain number, let's say 100 display points. And this is very, let's say, easy to interpret and read. So this is the FEA with the aluminum part. We can see that the aluminum part is, let's say, attached to the punch. Now it traveled more, the punch, instead of around 50 millimeters to around 60 millimeters. This is the strain, the stress, and the speed of the punch. The speed of the punch is very near to the initial speed, so it ended with around 200 meters per second. So this is the today's FEA scenario. You have the geometry file on our website, and feel free to modify it and edit and come up with new settings and analysis. Have a nice day and all the best.